This is lesson 2.1b, and we're going to talk about using derivatives. To find the equation of a tangent line. Okay, so a few things that we already know is that the derivative is what we refer to as f prime of x, and that is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x if the limit exists. We're going to talk about a couple of cases where the limit will not exist today, and about points in which we can't, x values in which we cannot take the derivative. Alright, so a few notation things. Alright, we know that this is f prime of x, we read that as f prime of x. Okay, some other ways that we can write that is we also write it as dy over dx, where d stands for difference. So the difference in y over the difference in x's, that's because derivative is slope. Because f of x is the same thing as y, we can write it as y prime. We could also write it as the derivative of f of x, or the difference in your y over the difference in your x, so we call that d dx of f of x. Sometimes you might see a capital D. That means the derivative of x with, the derivative of y with respect to x, alright? And actually you can, that's what all of these mean. We always take the derivative in calculus AB. We take the derivative of x with respect to y. Okay, so that's what all of that stuff right there means. Alright, so when we take the derivative, we call that differentiation. So sometimes you may come across some problems. It may say differentiate f of x. That means to find the derivative. So differentiation means to find the derivative. And the little heavy breather you might hear on this video is my dog, is Prissy. Alright, a function is differentiable. Differentiable. Good old SAT word. Everybody say differentiable. A function is differentiable at x if its derivative exists at x. Okay, and it is only differentiable on an open interval if it is differentiable highlighter either. If it is differentiable at every, I'm sorry, I'm laughing at my dog, at every point in that interval. Okay, differentiability. And continuity, they do not imply the same thing. Alright, but we do have to look at them together in this case. If f is differentiable at x equals c, then f is also continuous. That is a big theorem that they love to give multiple choice questions on in AP. Alright, so f is also continuous at x equals c. Alright, now the converse of that is not true. Okay, differentiability implies continuity. So if it's differentiable, then that means that it is continuous. Alright, but continuity does not imply differentiability. So the converse of this statement is not true here. Just because it's continuous does not mean that it's differentiable. Alright, that's because, and you can see some examples in your book, sometimes you may have a curve like this where you've got this sharp turn like that. Then at sharp turns, then this is not differentiable. So something like this, something like an absolute value, pretend those lines are straight. Alright, these points right here are not differentiable. Alright, some other things, remember that if it's not continuous, then it's not differentiable. So right here at this point, we would not be able to differentiate this function. Now, if we were to restrict our interval, say from this point to that point, then we can differentiate it from, on that interval or even on this interval, but we couldn't differentiate it on any interval that includes that hole right there. The same thing goes with the vertical asymptote. If you have something like your reciprocal function there, then right here where x is equal to whatever this value is, we could not differentiate it. Okay, so those are a few places where you can't differentiate. All right, let me see. One more thing, and then we're going to jump into some examples and talk about some of these things that I've already been talking about here. But along with your limit process for derivatives, we have an alternate form for finding the slope at a point. And this will just give it to you at one point. The key thing to remember here is that, if you are using this formula right here, then that means that you can find the derivative in terms of x, and that's a function that will give you the slope at any point, depending on what you plug in for x. That's what we did in the last lesson. All right, but the alternate form that I'm about to give you, it will only give you the slope at one point, and that is f prime of c, where of course c is the x value of that point, is equal to the limit as x approaches c of f of x minus f of c all over x minus c. Okay, so there again, that's your change in y's over your change in x's there. Okay, so let me show you real quick how we use that formula. Let's say that we want to find the slope of the function f of x is equal to 2x squared minus x plus 4 at the ordered pair, not negative 2, I'm sorry, at 2, negative 3. Okay, since we're, looking forward at just that one point right there, and, it's just asking for the slope, it's not asking for a derivative or anything, because your derivative would be f prime of x in terms of x, but it's just asking for your slope there at this given point. Then you can use this alternate form in which c is going to be 2. All right, so we can say that f prime of 2, that means that your slope at 2, or your derivative at 2, is equal to the limit as x approaches 2 of f of x, and in this case f of x is 2x squared minus x plus 4, minus whatever f of 2 is, all right? So, because we're putting 2 in the place of c, so we've got to figure out what f of 2 is. And that's what I'm going to do right here. I'm just going to plug in a 2 in the place of that x. Okay, so all of this right here is telling me what f of 2 is. All right, all of that right there is. Okay, and then this is over x minus c, which is 2. All right, and we're going to simplify this and take the limit, and that should come down to just one number, not a function in terms of x or anything. We should just end up with a number because we're looking for slope. So that's going to be 2x squared minus x plus 4. All of this right here works out to be what? That's 8 minus 2 is 6 plus 4 is going to give us 10. So that's going to be a minus 10 all over x minus 2. And we're going to find this limit by using some of those analytical techniques that we learned early on with limits. So that's 2x squared minus x minus 6 all over x minus 2. So I'm going to factor this right here. If you set this equal, if you go horizontally setting this equal, then you need to make sure you include that limit symbol. Otherwise, you might end up setting two things equal that really are not equal, and that's not a good thing. All right, so this factors into x minus 2 times 2x plus 3. All over x minus 2. And see right here, that's going to cancel. So our slope at 2, or our derivative at 2, is going to be the limit as x approaches 2 of 2x plus 3. We can now put 2 in the place of 2 by using direct sub, which means we can drop the limit symbol. We're not setting two things equal that really aren't. These are equal. So I can put 2 in the place of x right there, and then I can figure out that 7 would be my slope at that point. So what this alternate form does is it saves you some steps if you're just finding it at a single point. Now again, if it asks for just the derivative of this, then that has to be in terms of x. But this is asking for the slope of this function at that point. So we're good there.